In continuation with the previous session. So in the previous session, we were discussing traveling salesperson problem and how to solve this problem using dynamic programming. So as I have been discussing, the traveling salesperson problem is to determine a shortest path that starts and ends at vertex number 1, assuming that vertex number 1 is the starting city. But it is not compulsory that vertex 1 shall be the starting city. Any vertex can be considered as the starting city. But for simplicity and representation here, it is being assumed that the first vertex is the starting city. So whenever you have been given a starting city, the challenge is to find the shortest path through which all the remaining cities will be visited and the salesperson will return back to the vertex number 1. So if you see this graph, the traveling salesperson problem will be represented in the form of a directed weighted graph, where each vertex in the graph represents a city. So in the given graph here, there are 4 cities represented as 4 vertices. Then every 2 cities may be connected with an edge. So if you see, this is a fully connected graph where every city is connected to every other city. So this may not be true in all cases, in all the problems. Every 2 cities may be directly connected with an edge, or they might not be connected with an edge. That is also possible. Now, I'm assuming that vertex number 1, city number 1, is the starting city. Now, the problem here is that you have to find a shortest path through which you'll travel to the remaining cities 2, 3, and 4, and you'll return to the starting city number 1. So the path may be 1, 2, 3, 4. You'll come back to city number 1. So that may be the shortest route. Or you may travel to 1, 3, 2, 4, and 1. That may be the shortest path. So there might be multiple paths that may be available, but the challenge is to find the shortest path. Now, as I have been saying, the information of traveling salesperson problem will be represented in the form of a directed weighted graph. So here you can see edges are directed, and the direction indicates that you can travel from city number 1 to city number 2, as well as from city 2 back to city 1. So there are arrow marks on both the sides of the edge. That is, two-way traversal is possible. Two-way travel is possible. Then weight, each edge will be weighted, each route will be weighted. So because we're talking about traveling, so the cost of the edge will be equal to the distance between the cities. So between every 2 cities, there might be an edge, or there may not be an edge. If there is an edge, then the weight of the edge will be equal to the distance between the cities. Now, the cost function G, this cost function G will give you the length of the shortest path starting from vertex number 1, going through all the remaining vertices in the graph, and returning to vertex number 1. And such a path should be the shortest path, and the length of such shortest path is given by a cost function represented with G, where G will take 2 parameters. This cost function G takes 2 parameters. What is the starting city, comma, what are the remaining vertices through which travel needs to happen. So now, if I have to represent this, where I am considering that the starting city is 1. Then I am going to represent this as the cost function G, where the starting city is 1, comma, what are the remaining vertices, the remaining cities through which the route has to be determined. So that will be equal to the remaining vertices. Apart from 1, what are the remaining vertices? These are 2, 3, 4. I am writing this 2, 3, 4 as V minus 1. Because for the given graph, V is the set of vertices in the graph, and the set of vertices in the graph are 1, 2, 3, and 4. This is the V, the vertices in the graph. Now I have to write only 2, 3, 4. The subset of V. How can I write it? I can write it as V minus 1. So that is what is being written here. G is the cost function, 1 is the starting city, V minus 1 is the remaining set of cities through which the shortest path has to be found out. Further, this G cost function gives the length of the shortest path, or it gives the cost. It gives the cost of shortest path. Of the shortest path. Right now, how to calculate this cost of shortest path? Because there might be many paths. As I said, the path may be 1, 2, 3, 4, 1, or the path may be 1, 3, 2, 4, 1, or the path may be 1, 4, 2, 3, 1. So there might be many possible paths, many feasible paths. But how to find the shortest path and how to find out the cost of the shortest path? So for that, this is the formula that is using dynamic programming approach. This is a recursive formula because you can see that within the formula, there is a function, cost function G, which is written again by using the cost function itself. So a function calling itself will be a recursive function. So this is a recursive formula. So we are trying to solve the given problem using dynamic programming recursive approach. So what is this now? We have discussed what is this. G1 comma V minus 1. We have discussed what does this representation mean. But now what does this representation mean? What is G, K, V minus 1 comma K? This is generalization. This is generalization for this formula. Right now, what is this here? This is K indicates the starting city. K indicates the starting city. And V minus 1 comma K represents the remaining vertices. Remaining vertices. So out of V, you have already visited first node because it is the starting city. Then you have already visited K. Then the remaining nodes will be, apart from 1, city number 1 and city number K, the remaining nodes will be V minus 1 comma K. So this is a recursive formula. This recursive formula you will be able to understand. Then we'll work out some problem. You'll be able to understand how this formula gives you the length of the shortest path. So this is the given graph. The number of vertices in the graph. The list of vertices in the graph is 1, 2, 3, 4. This is the adjacency matrix representing the distance between the cities. You already know for a given graph how to find out the adjacency matrix. So the distance between city number 1 and city number 1 is 0. That is, the distance between a city to itself will always be 0. Then the distance between city number 1 and city number 2 is 10. The distance between city 1 and 3 is 15, and so on. This will be the adjacency matrix, or we can call it as a distance matrix that represents the distances between the cities. Now, given the graph and the vertices, we'll try to apply the cost function formula G, and we'll try to find out the shortest path and its length. So this is the formula. I'll start applying the formula in a recursive manner. I'll start with taking the first city as the starting city. So here I am taking city number 1 as the starting city. Now applying the recursive formula, cost function G, the starting city is 1. What are the remaining cities which are unvisited? Now you have to approach each city with a flag of whether the city is already visited or unvisited. Because in a route, within a route, each city has to be traveled to only one time, only for once. You have to visit each city only for once. Hence, each city will be flagged with either visited state or unvisited state. If the city is already visited, we'll not visit it again. So here the starting city is 1. So that means the city number 1 becomes visited. Then the remaining cities will be 2, 3, 4. You have to find a shortest path to visit all these cities 2, 3, 4 and return to city number 1. And as per the formula, the above given formula, I'm going to apply this formula. It is the minimum of values. What are the remaining cities? The remaining cities to be visited are 2, 3, 4. And this will be the possible values for some k, variable k. Now, the formula is C1k plus G of k, comma, V minus 1k. Right? So G of k, comma, V. V is 1, 2, 3, 4 minus 1, comma, k. Now, I have to expand this formula for different values of k. So I have here C1k. I have here k. I have another k here. Now, these k values have to be varied. Now, how can I vary the possible values of k? What are the possible values for k? K value can be 2 or 3 or 4 because these are the remaining cities that are to be visited. Now, in each of the k here, I have to replace it with 2. Then I'll have to replace it with 3. Then I have to replace it with 4. And I have to find the values, and whichever value is minimum, I'll take it. So what is actually happening here? If I want to find the minimum value, then there is a recursion here that you have to see. This is again your recursive formula. If I have to find out G of 1, 2, 3, 4, then I have to find out G of k, 1, 2, 3, 4 minus 1k. I have to find out this. Right? So this is a recursive formula. So what is happening here is, after visiting first node, that is the starting city is first one, the remaining cities are 2, 3, and 4. After visiting city number 1, I can visit city number 2, I can visit city number 3, I can visit city number 4. So what is the next city that you have to visit? There are 3 possibilities. After visiting city number 1, you may go to city number 2, you may go to city number 3, or you may go to city number 4. Now, to which city you will travel next, that depends upon the shortest path. From 1 to 2, it is shortest, or from 1 to 3 it is shortest, or from 1 to 4 it is shortest. Then if I choose that I'll travel to city number 2, then after visiting 2, the remaining cities will be city number 3 and city number 4. Now after visiting 2, what will be the next city I'll visit? It may be 3 or it may be 4. That depends upon which is the shortest route. Right? So as such, I'm going to follow the process of recursion and I'm going to find out the shortest route with the shortest distance. So starting with this, I'll try to replace the k here with the 3 possible values 2, 3 and 4. So this is the recursive formula. I have k here in the formula, which I'm going to replace with 2 first. So k will be replaced with 2. K will be replaced with 2. So C1k is becoming C12 plus g of k is equal to 2. Here k is there. This is 2. Then 1, 2, 3, 4 minus 1 comma k. K is 2. So 1, 2, 3, 4 minus 1 comma 2. That gives you 3, 2. Now you can see what is the meaning of this. The meaning of this here is that you have started at city number 1. Then you are checking the possibility that the next city you will be traveling is 2. The next city that you'll travel is city number 2. So here then if you have to travel, if you have decided to travel to city number 2, then what is the distance between city number 1 and 2? It will be C12, the weight of that edge that represents the distance between 1 and 2. So this is here C of 1 comma 2, the distance between city 1 and 2. Then you have visited city 1, then you have visited city 2. Now what are the remaining cities that you have to visit? 3 and 4. Now this 2 becomes the starting city. The remaining cities that you have to visit will be 3 and 4. And this problem is a sub-problem. And this sub-problem can be now represented as g of 2, because 2 is now the starting city. The remaining cities to be visited are 3, 4. So this is the cost function for the sub-problem. That is what I have written here, g of 2, 3, 4. 2 is the starting city, 3, 4 are the remaining cities. G is the cost function, which gives you the length of the shortest path. Now, k I have represented with 2. K I have replaced with 2. There is another possible value for k. After visiting city number 1, I can visit city number 3. That possibility is also there. So after visiting city number 1, I may decide to visit to city number 3 next. If I'm visiting city 1 to 3, then what is the distance between 1 and 3? It is C13. That is what I have written, C13 plus, now this 3 becomes the starting city. Now, what are the remaining cities that need to be visited? The remaining cities that need to be visited are 2 and 4. This is again a sub-problem, which can be represented as G of the starting city is 3. The remaining cities to be visited are 2, 4. So what am I doing here? By using recursion, I am trying to divide the problem, the main problem. I'm trying to divide it into sub-problems using recursion. Now, that is what I have written here. G of 3, 2, 4. 3 is the starting city. 2, 4 are the remaining cities that I need to visit. So in the same way, after city number 1, I may decide that I'll visit city number 4. Then the cost of traveling from city 1 to 4 is C14 plus 4 becomes the starting city now. And 2, 3 will be the remaining cities. I have to now find the shortest path starting from 4 to the remaining cities, 2, 3. Now again, you can see that this thing is again recursive. G of 2, 3, 4 is again recursion. So I have to call it. Now, what are the possible values for K here? Possible values always for K. Possible values are the remaining cities. So here, the possible values for K at this level are the remaining cities, which are 3, 4. So K may be replaced with 3, K may be replaced with 4. So now then it will become C of 2, 3. That is the cost from visiting second city to third city. Plus, now third city will become the starting city and the remaining nodes to be visited equal to 4. Or I can take up an alternative where after visiting second city, I'll visit fourth city, and then the cost of traveling from 2 to 4 is C to 4 plus now the starting city will be the fourth city, remaining cities to be visited will be 3, and this you have to recursively go on building the recursion tree. Finally, it will come here, something like this. For this, where there will be some starting city 4 maybe. The remaining cities to be visited are null. There are no remaining cities to be visited. That is, you can observe the paths here. I have started with starting city number 1. Then I have decided to go to city number 2. Then I may have decided to go to city number 3, then to city number 4. So I have traveled 1, then 2, then 3, then 4. So now there are no remaining cities left out. This is one possible path. This is one feasible path. The other path will be, I'll start at 1, then I'll visit 2, then I'll visit 4, then I'll visit 3. So I have visited 1, 2, 4, and 3 in that order. So now there are no remaining cities to be visited. So I have shown you here 2 different paths, 2 possibilities. That is 1, 2, 3, and 4. Another path is 1, 2, 4, and 3. So if you also expand the remaining branches, you'll get maybe around 6 different paths that might be possible. 6 different paths that might be possible for a given problem. Now, if you have 6 feasible paths, now which is the optimal path? The optimal path is the one that is shortest, right? So for that, to find out the shortest path, you'll have to find out the distance of the routes. And for that, now you have divided the main problem into sub-problems in a top-down manner. Now I'll try to find out and calculate the lengths of the routes in the bottom-up approach. From bottom, I'll go to the top in the tree. I'll try to find out the length of each path. So for that, I'll show you one. The remaining lengths can be calculated in the same procedure. And for calculating the lengths of the routes, I will be needing the distance matrix. Now, this is the tree that I have formulated. One branch that I have taken, k is equal to 2. This path I am taking, k is equal to 2. This leftmost branch I am taking, and I am trying to calculate the length. So this was the left side branch with k value equal to 2. Now I'll start calculating the lengths of the paths from bottom to top. So I'll start at the bottom. G of 4, null. That is, there are no remaining cities to be visited. When there are no remaining cities to be visited, what will I do? I'll return to the starting city. So I'll have to go back to city number 1. So for that, whenever I am writing 4, null, that means it is the distance from 4 to 1. That is, this is C34 plus this will be C41. Traveling from the last city to the starting city. So C34 is 12. C41 is 8. So the value that comes here will be 20. So the value that comes here will be 12 plus 8, which is 20. So in the same way, this also I'll try to calculate. This is C43 plus this is C31. Now C43 is 9. C31 is 6. 9 plus 6, the value will be 15. Now traveling to the top side of the tree. Now I'll have to calculate C23 plus G of 3, 4. So that I'll calculate which is 9 plus 20. 9 plus 20, how did I get? G of 3, 4 value is 20. C23 value is 9. So this is 9, this is 20. Now, this on the right side is C24. C24. C24 is 10. C24 here is 10. And G of 4, 3, I have found out which is 15. 9 plus 6 is 15. So I'm going to get 10 plus 15. Now, I'm going to calculate this one here. C12. C12 value. C12 value is 10. And then G of 2, 3, 4. You have two values coming from the child. This one is 29. This one is 25. Now you have to take whichever is the minimum value. The value coming from the left side path is 29. The length of the right side path is 25. Whichever is the shortest path that you have to take. So this will become C12 value is 10 plus out of 9 and out of 29 and 25, whichever is shortest, take that value, which is 25. So you are going to get 35. It is the value 10 plus the minimum of the left side path or the right side path, whichever path is shortest, that you will take, and this is 35. Okay, now I have found out these values on the left side branch where K value is 2. Now you'll have to find the values for K is equal to 3. K is equal to 3. I have to find out. And the path length I have got is 40. In the same way, I have to find out the length of the path where K is equal to 4. And I have found out that it is 43. Now find out what is the shortest route of G, 1, 2, 3, 4. It is the minimum of these three values. 35, 40, 43. The minimum of these three values, which is 35. So this is the shortest path coming here onto the left side. How did I get 35 here? Which path gave me the shortest route of length 35? So for that, this is the route that gave me the shortest length 35. And I can say that now the shortest route is 1, 2, 4, 3, 1. This is the order of visiting the cities. I'll first start from city number 1, then visit 2, 4, 3, and return to city number 1. And the length of this shortest route is 35. So this is how you can represent. From starting city 1, I'll go to 2. From there, I'll go to 4. From there, I'll go to 3. Then return to 1. And these are the costs of the edges from the distance matrix, which is 10 plus 10, 20, 29, and 35. This is the shortest path available for traveling in the given graph, starting with the city number 1 and visiting the remaining cities 2, 3, 4. You may take up the same problem with a different starting city. Instead of taking starting city as 1, you can start from 2, or you can start from 3, and you can try to find out the shortest route. So the same process which I have represented using recursion tree, the same process can be represented in a mathematical model in a series of steps. Where I'll have 4 steps here, because the number of vertices are 4. I'll have to go through 4 steps. Step number 1 is where I'm trying to find out g of 2, 5. This is nothing but, so if you see this figure, what am I doing? First, I'm trying to find g of 4, null. Then I'm trying to find out g of 3, null. Then right side, if I draw the full figure, I'll be finding g of 2, null, 1, null. Then I'm trying to find out g of 3, 4, g of 4, 3. So this is your step 1. This is step 2. This is step 3. This is step 4. So in the same way, instead of drawing a figure, instead of drawing a recursion tree, you can write it in steps. Anyway, you'll get the same shortest route. And this is the algorithm for solving TSP using DP, where S is the starting city, V is the input cities, distance matrix represents the distances among the cities. And the result of this algorithm, the output of this algorithm will be the cost of the shortest route. Now, as I said, every city has to be visited only once. So you have to keep a flag for each city, whether it is visited or whether it is not visited, so that you can make sure that every city is visited only once. And for that, I'm keeping an array of flags for each vertex. I'm maintaining whether this vertex or whether this city is visited or not. If the city is not visited, it will be represented as a 0. If the city is already visited, its value will be equal to 1. Then I'm going to initialize the cost of the shortest path, because I have not yet started calculating. So the initial cost of the shortest path will be equal to 0. Then further, I'll try to visit different paths. I'll try to find out all the possible routes. I'll calculate the length for each route, and I'll find out the shortest route. So I'll start with starting city S. So once I reach a city S, I'll make its flag to visited. Visited means the flag should be equal to 1. Now S city is already visited. Then whether I have to go to the recursive formula or not. So I'll continue my recursion or I'll stop the recursion. So when you'll stop the recursion? You'll stop the recursion when, if you see this figure, if you see this g of 2, null, right? So if there are only 2 cities in the cost function, then I'm going to stop the recursion. So for that, this is the formula. If the number of vertices, the number of cities in the cost function are 2, then I'm going to stop the recursion. I'm going to find out the cost and return the cost. Otherwise, in the cost function there are more than 2 cities, then I'll have to apply recursive formula. This is the recursive formula. Distance of ij, that is Cij, plus the G cost function. Now J will become the starting city. This V minus I will be the remaining cities. And this is the recursive formula. And this is the time complexity of the algorithm. Big O of V square 2 power V, where V is the number of cities. So this was this session on solving traveling salesman problem using dynamic programming using recursion. So I have discussed in today's session, given a problem, how to solve the problem using dynamic programming using recursion. Further, I have presented to you the algorithm and the time complexity of the algorithm.